All right, good evening. Welcome back to trigonometry, and we are going to be talking about graphing. Now, in the previous video, we talked about graphing things like y is equal to sine x, y is equal to a sine x, and y is equal to a cosine x. Talking about the fact that this a is the amplitude. It's a vertical stretch. If it's bigger than 1, it's a vertical compression if it's between 0 and 1, and it's a reflection about the x-axis if it is negative. Okay? Now we get to deal with the fact that we don't have functions like this all the time. We might have to generate a lot of different pieces. So we'll start off with something like this, where we have sine of, say, bx. Okay, and this b, if b is greater than 0, okay, we're going to be shrinking this frequency down. Okay, um, to get the frequency, to get the wavelength, the book recommends that we used a capital B, I guess. The book recommends you use this formula, 2 pi over b, and for sine and cosine, that's the formula you use. Sine, cosine, secant, and cosecant, actually, 2 pi over b. And you are more than welcome to memorize that formula. But we also have something called a phase shift, which is like an A, we get rid of the y equals sine of x minus c. Okay, and remember from college algebra that this minus c was a shift to the right. Okay, but this is going to get a little bit more difficult because what if we had something like y is equal to the square root of, say, 5x minus 3? And it's the question that you're trying to figure out. Okay, we know what the parent function looks like. We know that there's a shift to the right by 3. But there isn't really. You have to do one more thing to it, and that's going to be, this is the square root of 5x minus 3 over 5. It's actually it's a shift of 3/5 to the right, not a shift of 3. Because really the question you're asking is, where is the starting point for this graph? And if we figure out the starting point, it's 5x minus 3 is equal to 0, right? That's where we want to go deal with that. So we would say, okay, this is 5x equals 3, x equals 3/5. My starting point is 3/5. So here's my 3/5 in order to graph my square root function. Okay, so you have to be a little bit careful with this. If you have a sine of, say, bx minus c, the reason why the phase shift looks the way it does is because we have to do this too. We have to say this is sine of b, x minus c over b, and your phase shift is the c over b. Okay? I'm going to show you a slightly easier way to deal with all of this, including the period, so that you can figure it out that way without having to memorize extra formulas. Okay, and it's all going to hinge on the fact that we had these anchor points from the last lesson. Okay, remember our anchor points are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Because when I go to graph my function, we're going to say, okay, there's my 2 pi, and then halfway through, that's my pi. Halfway through, that's pi over 2. Halfway between pi and 2 pi was 3 pi over 2. And then for, say, something like y is equal to 3 sine x, 1, 2, 3, 1, 2, 3. And we're going to be able to say, okay, it's 0, right? We are at sine of 0 is 0. 3 times that is going to be that. So we're going to be up here at 1, at 3 rather, back down at 0. Okay. Sine of 3 pi over 2 is -1. 3 times -1, we end up with -3, and then we're back to 0. So we can go ahead and type in these points here, pretend this looks pretty, okay? And go ahead and have a graph. Yeah, it looks terrible, but pretend it looks nice. All right. So usually when you have these problems, graphing trigonometric functions, you are asked to plot or asked to identify 5 different points on your graph. 1, 2, 3, 4, 5. What a coincidence that there are 5 anchor points, and you're always asked to identify 5 points on your graph. I sense a connection here. So that's what we're going to do. Every time we're going to be able to solve something, we're going to plot those anchor points, or at least the anchor points adjusted for that particular function. Okay, so here's what we're going to do. And you are more than welcome to use the one in the book. It doesn't matter to me. I want you to use whichever way you find to be easiest. I find this way to be easiest because I kind of came up with this because when I was sitting in your chairs, I was like, I'm not memorizing 2 pi over b and then trying to deal with a fate. I'm never going to remember this. But here's another way to go. So we're going to try to graph y equals 1/5 sine of 2x minus pi over 3 plus 1. This is all of the different features on our graph for us to figure out. Okay, that's the whole thing. So what I'm going to do is I'm just going to write this guy down over here. So we have y equals, what is this, 1/5? Let me double make sure. 1/5 sine 2x minus pi over 3. Okay, sine of 2x minus pi over 3. And then we had a, what was this? This was minus 1 at the end. Let's see, plus 1. Okay, plus 1. Okay, so what we're going to do is I have to solve 5 linear equations. I know it sounds like a lot, but I have faith in you. I know you can do this. So what we're going to do is I want to know what x has to be so that this 2x minus pi over 3, 2x minus pi over 3, I want this whole argument to be equal to 0. How do we do that? We set it equal to 0 and we solve for x. So let's go ahead and solve it. We have 2x equals pi over 3. I just added pi over 3 to both sides, divide both sides by 2, and we'll say x equals pi, right? Dividing by 2 is the same as multiplying by a half, is pi over 6. So when x is equal to pi over 6, this argument is going to be 0. Let's test that out. So if I have sine of 2 times pi over 6 minus pi over 3, let's go ahead and evaluate that. That's 2 times pi over 6, right? And 2 pi over 6, that's actually pi over 3. So we end up with pi over 3 minus pi over 3. If I didn't know any better, I'd say that was 0. Okay, so when x is equal to pi over 6, and I plug it back into this argument, we end up getting 0. I would have to take, what's the sign of 0? Well, I know what that is. It's 0. I know what the sign of pi over 6 is too, but we might get some weird angles in here that I don't really know about. But I know that when I plug this back into my function, I get a nice number to graph. So one of my anchor points is going to be when x equals pi over 6, because that argument is going to make this whole sine function equal to 0. Right. Let's do the next one. So we have 2x minus pi over 3. What's my next value? Is pi over 2. What does x have to be so that this argument turns into pi over 2? So let's go ahead and solve that. So we're going to set that's a semicolon. We have 2x equals pi over 2 plus pi over 3. Oh no, we have to get common denominators. 3 over 3, 2 over 2. So we're going to say 2x equals, this is going to be 3 pi over, what is this, 6 plus 2 pi over 6. So that's going to give me 5 pi over 6. So 2x equals 5 pi over 6. And I've got one more thing to do, and we're going to say divide both sides by 2. So that's going to be x equals 5 pi times a half, right? That's going to cancel that, times a half. That's going to be 5 pi over 12. When x is equal to 5 pi over 12, okay, so when x equals 5 pi over 12, what is the value of y equals sine of, what is this, 2x minus pi over 3? And let's go ahead and figure that out. Okay, so we're just trying to make sure that we're doing the right things here. So I'm going to go ahead and plug in my 5 pi over 12. So we have sine of 2 times 5 pi over 12 minus pi over 3. Okay, we're just going to figure this out. So we want, this is going to be 10 pi over 12. We can cancel some stuff, right? This is the sine of, that cancels a little bit. So we have 5 pi over 6, right? 2 is 2 over 12, minus pi over 3. Let's go ahead and get some common denominators. So that's going to be sine of 5 pi over 6 minus, if I multiply 2 over 2 here, right, that's going to be minus 2 pi over 6. 5 pi over 6 minus 2 pi over 6. That should be the sine of 5 minus 2 is 3 pi over 6. If I didn't know any better, I would swear that that's the sign of pi over 2. What's the sign of pi over 2? Oh, it's 1. We should know that. And that's how I'm going to go through and do all of these little problems. So the 5 problems I'm going to do is I'm going to take this, what does I have here? We have 2x minus pi over 3. So I'm going to say we have 2x minus pi over 3 equals 0. Solve for x. 2x minus pi over 3 equals pi over 2. Solve for x. 2x minus pi over 3 equals pi. Solve for x. 2x minus pi over 3 is equal to 3 pi over 2, right? That's my third anchor point. And then my final anchor point is 2x minus pi over 3 equals 2 pi. That's 1, 2, 3, 4, 5 linear equations. We can handle that. They're linear equations. They're not fun, but these are not hard problems. So I'm going to go ahead and say that this is going to be 2x equals pi over 3. Multiply both sides by 1/2, and we end up with x equals pi over 6. That's my first anchor point. 2x minus pi over 3 is equal to pi over 2. We're just going to go ahead and solve that. It's 2x equals pi over 2 plus pi over 3. We just did this one. That's 2x equals 5 pi over 6, which is also, or x is equal to 5 pi over 12. Okay? I'm going to do one more thing when I'm tabulating these little things. I'm noticing there's just 12 here. These are always going to come up with a pattern. They're always going to form a pattern. And this pattern is always going to be the second one that we're going to be dealing with. The linchpin on this one is going to be the second piece. So we have 2 pi over 12. Let's do the third one. So we're going to say this 2x minus pi over 3 is equal to pi. We have 2x equals 3 pi over 3. That's a fancy way to write 1 pi plus 1 pi over 3. That gives me 2x equals 4 pi over 3, 3 plus 1. And then we divide both sides by 2, and we say x equals 4 pi over 6. And say for a minute, I'm building something I don't want to reduce because I'm trying to look for a pattern. We'll reduce later, but we're going to hang out with this. Let me go ahead and multiply it by 1, 2 over 2. And that gives me 8 pi over 12. So far we have 2 pi over 12, 5 pi over 12, 8 pi over 12. Do you sense a pattern? I feel like Dora the Explorer at this point, but do you sense a pattern? I suspect you do. Okay. Let me see if I can guess the pattern here. So it looks like we're adding 3 pi over 12 every time. Let me just write this down and say, I bet we are going to have 11 pi over 12 on the next problem. And let's test that out. It'll work. So we have 2x equals 3 pi over 2 plus pi over 3. We have to get common denominators. So we're going to say 3 over 3 and 2 over 2. That'll give me a common denominator. So we have 9 pi over 6 plus 2 pi over 6, right? And that's we have 2x equals 9 plus 2. That gives me 11 pi over 6. Divide both sides by 2, and we get x equals, what do you know? It's 11 pi over 12. I guess my pattern was correct. Okay, but you can do it either way. You can either form a pattern and kind of, I'll say, guess the next term because it's always going to be that pattern. Okay, or you could just solve the 5 different equations you have here. You could also do it the way the book says to do it and get the period, get the phase shift, and then figure it out that way. And that's fine. You're allowed to do it either way. I don't really care which way you do it. Use which way is the most comfortable for you. This is the way that's most comfortable for me because, frankly, at this point in my education, linear equations aren't scary. I mean, if you give this to like a beginning algebra student, this is terror, right? They won't be this is a thing out of nightmares. This is not good. But you, taking trigonometry, you've been through that. This isn't too bad. Pi is not a scary number. It's just a number. So we're going to say this is 2x is equal to 2 pi plus pi over 3. Oh, now I got to get common denominators. This is 2x equals, I'm going to multiply this by 3 over 3. We're getting common denominators. 3 times 2, that's going to be 6 pi over 3 plus pi over 3. That's going to give me 2x equals 7 pi over 3. And then we have to divide by 2, right? We get x equals 7 pi over 6. But remember that our pattern is in twelfths, so I have to multiply by 2 over 2 to match up my pattern. 7 times 2 is 14 pi, and 6 times 2 is going to be over 12. So here's my collection. We have 2 pi over 12, 5 pi over 12, 8 pi over 12, 11 pi over 12, and finally 14 pi over 12. There's a pattern. Each of these is different by 3 pi, or 2 pi rather, or 3 pi over 12. Okay, so when I go to graph, those are the points that I want to have labeled. Okay, so we're going to say here's my 14 pi over 12, and then here is my pi over, what was it? It was 2 pi over 12? 2 pi over 12. So here's my 2 pi over 12. My middle term, and you can do this in a number of ways. You can go back up and look, but if you average these together, right, we have 2 pi over 12 plus 14 pi over 12. That's going to be 16 pi over 12 divided by 2. That's going to give me, I think, 8 pi over 12. So that was my middle term. That was my 8 pi over 12 here. Okay. So you can either average them together, or you can keep better notes than I did and kind of think what's going on. Again, we're averaging these two guys together, just adding them together and dividing by 2, or adding them together and dividing, multiplying by a half. But we're going to end up with 5 pi over 12. Okay. And then we're going to have what's the last, 11 pi over 12. 11 pi over 12. I never writing 11 pi over 12. But those are my anchor points. Now, I need one more little thing to deal with, because this is not the function that I started with, right? I stripped out all the stuff. I stripped out the +1. I stripped out the 1/5. Let's put it back in the actual thing so that I have my collection of anchor points, but let's go ahead and deal with it this way. So that's my 0. I don't really want 0, because what does this +1 do for me? Okay, it raises the whole graph up by 1 unit. So everything gets to go up by 1. So we're going to go up here to 1. Okay, and that's the one I'm actually going to deal with. Actually, let me change this. Let me go ahead and draw my axis here. There's my axes. Okay, my x-axis. And then I'm going to dot this one in at y equals 1. And here, my sign is going to dance around what this is. What is my amplitude? My amplitude is 1/5. So what is 1 plus 1/5? Well, 1 is 5/5. 1 plus 5/5 plus 1/5 is equal to 6/5. 1 minus 1/5. So we have 5/5 minus 1/5. 5/5 minus 4. 5/5 minus 1/5. We end up with 4 over 5. So we have my amplitude, my center line is at 1. We go a fifth above, we go a fifth below. And let's go ahead and take these guys in. So we're going to say this is going to be my 14 pi over 12. My halfway through here, that was my 8 pi over 12. I'm just looking at the ones right above it. This was my 2 pi over 12. You don't have to reduce. We want the pattern. Okay, we have a 5 pi over 12. And then we have an 11 pi over 12. And now we're going to dot in our function. I'm sorry, we're going to dot it in here, and here, and here, and here, and here. So my function is going to look something like this. And I know that it's going to go dot, dot, dot in both directions, but since there's an obvious pattern here, I could keep, if I needed to do 2, it's like, oh, 2, 5, 8, 11, 14. I'll bet that 17 will be the next one, 17 pi over 12, then 20 pi over 12, then 23 pi over 12, dot, 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 for as long as you wanted to go. We could also go beforehand. We could just keep subtracting 3 pi. We can go as long as we wanted to go in the negative direction. Doesn't matter. But that's how I like to graph functions. I like to graph sines and cosines. that have all of these different elements in it, they're also going to ask you like, hey, what's the wavelength? Well, I know that the end point is 14 pi over 12, and the beginning point is 2 pi over 12. Let's go ahead and subtract 14 minus 2. That's going to give me 12 pi over 12, which is just pi. I'm going to ask you, like, do you remember what the period function is? It's 2 pi over b. What the heck was b? When I go all the way back up here to look at my b was 2. Okay, so b is 2. So we have 2 pi over 2. Hey, the period is pi. What do you know? These match up. They're exactly the same thing. I can say last minus first, right? The end minus the beginning, alpha minus omega, if you will. Uh, or sorry, omega minus alpha, as it were. But we're going to get the same thing. If I do the whole, the 0 to 2 pi in my coordinates, I'm going to get the same wavelength. What's my phase shift? Okay, back here, you. Okay, I know that I should have started with 0. I did not start with 0. I started at 2 pi over 12, which reduces to pi over 6. If I go back and look at my phase shift, which is going to be, what is that, C over B? Remembering that? What's my C? All the way back up here, that was, I guess, pi over 3, and we're going to divide it by 2. So we're going to divide, we have pi over 3 divided by 2, or pi over 3 divided by 2, pi over 3 times 1/2, invert and multiply, gives me pi over 6. So I also know what my phase shift is, knowing where I should have started, 0, and where I actually started, pi over 6. So I know what my phase shift is. I know what my period is. I have a good graph with 5 points labeled, which is usually the question that they're asking. I can tell you my amplitude is 1/5. Like all of that stuff comes out of the process of graphing it, where I didn't technically have to memorize these formulas. Some of you guys are dying to memorize stuff. You can memorize this if you'd like. It's okay. And if you find it easier to do it that way, then please do it that way. But I didn't like to have to memorize stuff. And for those of you who are going on to calculus and like physics, you're going to have to, in calculus, you have a ton of stuff you're going to have to memorize. Okay, you have to memorize all of the calculus rules for all of the trig functions, and then you have to do them forwards and backwards. You want to go on to physics, you got to do F equals ma, you got to do V equals IR. There's just a lot of stuff that there is to memorize. Chemistry, PV over T, or PV equals nRT for your ideal gas law. P1 V1 T1 equals P2 V2 T2. I mean, if you're going to be a science major, there's a ton of stuff you have to memorize. I would prefer to minimize that and only have to memorize the stuff that I really have to. I never had to memorize this because I can just kind of work it through. Does it take me a little longer? Yeah, it does. Okay, but I don't have to memorize stuff. And even in trigonometry, there's going to be other formulas that we are going to have to memorize. Okay. Eventually, when we get to chapter 6, you're going to have to memorize law of sines. You're going to have to memorize law of cosine. Law of sines is easy to memorize. Law of cosines is a little bit more, okay? But there's a ton of stuff that you have to memorize. I just don't like to do that all the thing. If you want to memorize it, you go right ahead and do it. I don't want to. So that's my way of figuring out how to graph these functions that have all these different little elements in them, and I can kind of backtrack and get my phase shift and my period and everything, all the points that I want to get, all that stuff comes out. Okay. So I will do more examples with this because this is not let me show you once and then you've got it. Like that doesn't happen. This takes a couple of times seeing it and it takes a few times doing it. Okay. So I urge you, practice these things. Okay. So that you can get the anchor points to hang your graph on and be able to do that. You guys know how to use Desmos. You can type in a function in the Desmos and see if your graph matches Desmos's graph. So the kind of function you're looking for is a sine bx minus c plus d. The numbers you want to pick for A, B, C, and D are integers like between -7 and +7. Okay. So, you might pick a half. That's okay. It's not an integer, but it's like an easy fraction, like a half, a 2/3, a 4/5, easy fractions or integers, and that's all it's going to have to be. I'm not going to ask you, and the book is going to ask you. We've got, 1/5 sine of, say, the natural log of 5x minus something crazy, the square root of 29 um, over pi plus, and then some crazy number like e to the 3/2 power, and then you have to graph. But that's not going to happen. I'm not going to do this to you because I don't want to grade this, and this is going to be too much. So pick integers for your A, B, C, and D, and practice. Check it in Desmos and see if you're doing it the right way. There will be more examples here. So thank you very much for watching all of that to the end, including all of my rant about the memorization. I'm sorry for that, but you have enough to keep going with this. So I'm going to go ahead and post this to your shell, and I will do another few of these every once in, maybe every day for a while until we have enough examples so that you feel comfortable practicing this stuff and you learn how to do it. So I'm going to stop here and say, go do some homework. Thank you very much for watching, and good luck with practicing your graphs.